to build a chamber where the gas at my feet is minus 270 degrees centigrade, but up here it's 300 million degrees centigrade. That's hundreds of times hotter than the surface of the sun. And it's when the gas gets that hot that the atoms crash into each other, releasing huge amounts of energy. The fuels that are used to create this super energy are found all over the planet. Hydrogen gas is the most plentiful element in the universe, and on Earth you can't really escape the stuff. It's one of the two substances that make up water, so there's a nearly limitless supply. The other fuel used to power the generator is lithium, one of the most common metals found in the Earth's crust. So if scientists can make fusion work, there's the prospect of huge amounts of power for thousands of years to come, using only a tiny amount of fuel. You only need 1/10 of a gram. That's about what this pin weighs. This minute amount of fuel generates a vast amount of power, 16 megawatts. That's enough to run 16,000 electric fires.
At JET, basically, we've been able to show that fusion works and we can make fusion reactions. What we have to do in the future is to build a bigger experiment and actually show that we can generate electricity on a commercial scale.
The problem for scientists at JET is that they've only been able to produce fusion for several seconds. Although that's better than anywhere else in the world, it's still not enough. For fusion to be a realistic source of energy, they've got to keep the reaction running. And that will be the next challenge.
Well, I have with me here the director of JET, the man who's leading the efforts to make this possible, Dr. Martin Keilhacker. You've managed to create fusion for several seconds, which is very impressive, but it sounds like you've still got a long way to go.
Well, you are right. It is difficult to produce fusion on a large scale, but we are very pleased with what we have achieved so far.
Well, we'll be talking more later on in the program, but first of all, back to Philippa.
Now, one of the reasons the JET lab is so advanced is because the scientists here need to create incredibly high temperatures before fusion can occur. So imagine the stir within the scientific community 9 years ago when two scientists claimed to have created fusion at room temperature, known as cold fusion. The two scientists were Professor Martin Fleischmann from Southampton University and Stanley Pons from the University of Utah. Back in 1989, Peter McCann and Judith Hahn looked into these claims.
You have a test tube of heavy water, that's water containing deuterium, and a couple of electrodes. The straight one here is made of palladium, and the coiled one is platinum. Now they're connected to a power source, and you also have a means of measuring the temperature in the cell. This weekend, we visited the laboratory where these experiments took place. Martin Fleischmann and Stanley Pons claimed this simple electrolysis setup, although not producing the neutrons normally released by fusion, had generated far more heat than they could explain. In one experiment, they say the palladium electrode actually melted.
We cannot explain the amounts of heat that come out by any chemical means or any other physical means other than a nuclear reaction. The amount of heat we measure is 1 billion times more than you would expect from the number of neutrons and other particles which we measure. So there is another reaction going on. I mean, I think it has to do with the deuterium-deuterium fusion reaction, but it is not the conventional deuterium-deuterium fusion reaction as we know it at high temperatures.
So Fleischmann and Pons claim to have achieved a totally new type of nuclear reaction, producing almost no neutrons.
But within a few days of the news from Fleischmann and Pons, there was another surprise announcement. A second group claimed that they'd produced fusion in a test tube because they detected specifically the neutrons, which theory predicts fusion should produce. This second group were just a few miles away at Brigham Young University, led by Dr. Steve Jones.
If fusion occurs, in particular involving deuterium, a type of hydrogen, then there is a neutron given off with a characteristic energy, 2.5 million electron volts. If we see that neutron, or many of these neutrons with just that energy, then it's a signature for fusion. Now, the electrochemical cell itself is extremely simple. Perhaps you can see the bubbles forming. Oxygen forms at the positive electrode, which in our case is gold.